So generally speaking, and we'll go into more detail about this, but you have your intrinsically safe device that's in the hazardous area. So whether it's gas, dust, or filings or whatever, you got your device that's there. As we've mentioned before, it has to be rated for intrinsically safe. And then those signals are brought back to the safe area. And I noticed there's a sealed separation. So wherever you have a penetration from a hazardous area to the safe area, there has to be sealing. It has to be sealed so that there's no possible penetration of the hazardous substance into the safe area. And then you'll run that through an intrinsically safe barrier or isolator, and then that signal goes to your control equipment. So the barrier or isolator provides that isolation between the hazardous area and the safe area. And this goes to just a couple different types. Shane, you want to talk about these? These are yours.
Yep. So just to be quick, all of us probably have heard the term Zener barrier and galvanic isolator, but there is a big difference between them. With the Zener barriers, they're essentially using something called a Zener diode, as well as a resistor and a fuse, and sometimes multiple components of those just for extra safety. But it's to make sure that if we ever have a situation where too much voltage is trying to come down the path out to the unsafe area, the hazardous area, the Zener diode will drop that to ground. And so it needs to have a very, what we call an intrinsically safe ground, less than 1 ohm between the barrier ground and the actual plant ground. But then there's also a resistor, so we don't ever have a situation where we could have an overcurrent situation. And there's also a fuse, so we don't have a situation in the field that could ever cause the barrier to be stressed as well. So we're really hitting it from 3 angles, and so it gives a lot of extra protection there. The galvanic isolator, on the other hand, there's no need for that intrinsically safe ground. It specifically creates essentially an air barrier because it's almost like a transformer where it's creating an actual separation with a galvanic isolation between the hazardous area and the safe area. So 2 different methods to do it. Generally, barriers are much cheaper, but require a little bit more electrical engineering to get it right. Isolators cover over a load of sins, but they typically cost about 2 to 3 times more.
Yeah, and just as ICA, we have a tendency to go toward the barriers, particularly in a retrofit, because if the overall plant and the systems were not designed, to provide that earth and all the other things that you need, it's a simpler installation, even if it does cost a little bit more. And so, yeah, basically there's 2 different types of intrinsically safe devices. There's the simple apparatus. You want to talk about that, Shane, again? This year's?
Yes. Simple apparatus would be something that will never be able to either store or generate too much of an electric type ignition that could cause a problem. So you're talking about typically thermocouples, some buttons, switches, LED lights. Those sorts of things are all simple, meaning that they don't have to be approved to be intrinsic safe. You could just go with an off-the-shelf unit and then apply an intrinsically safe barrier or isolator to it, and that would make the system be intrinsically safe. That is not true, though, when it comes to other things like transmitters, other types of lights. Certain other things have to be approved and tested that they can't electrically or thermally cause an ignition situation to occur. So they must have the approval by an approval body that says, this is an intrinsically safe transmitter, as an example, and it must be combined with a barrier isolator and the right calculations for the cable to make sure that the system as a whole in total is an IS system.